Every time you wash your hands, you witness a stunning display of advanced mathematics, perfectly executed. The delicate, shimmering surface of a simple soap bubble is actually a complex geometric marvel, constantly optimizing its form. These fragile spheres effortlessly solve incredibly intricate calculus problems in milliseconds, right before your eyes. Imagine a tiny, transparent architect building the most efficient structures possible using only air and a thin film. Soap bubbles are far more than just childhood toys or fleeting moments of joy. They represent one of nature's most elegant demonstrations of mathematical principles at work. Understanding their behavior reveals profound insights into energy, geometry, and fundamental physical forces. The science behind these ephemeral structures has captivated thinkers for centuries, from scientists to artists. Every individual bubble and every complex cluster follows precise, predictable rules governing its unique shape and stability. These underlying rules are not arbitrary. Instead, they represent the fundamental laws of geometry and energy minimization. Nature consistently seeks the most efficient path, and soap films provide a crystal-clear example of this.
This pursuit of efficiency dictates everything from the bubble's initial spherical form to its eventual collapse.
Island, simplest soapy constant film, is a living negotiation between the diagram of internal air pressure and the external sophisticated forces of surface tension. Collapse, therefore, simplest soapy constant film, is a living negotiation between the diagram of internal air pressure and the external sophisticated forces of surface tension, mathematical solutions. These hidden patterns are surprisingly present throughout your daily life, not just in a sudsy sink. The most basic mathematical pattern is the sphere, which every individual soap bubble naturally adopts. A sphere is the only shape that encloses the maximum volume of air with the absolute minimum surface area. This geometric efficiency minimizes the energy required for the soap film to maintain its structure. It's like a tiny, self-optimizing balloon, always striving for the most relaxed and stable configuration possible. But that's not the strangest part. Things get truly fascinating when multiple bubbles interact. When two bubbles meet, they merge their walls, creating a shared surface that's perfectly flat.
This flat wall always forms a precise 90-degree angle with the plane tangent to the spheres at the intersection point.
Furthermore, three soap film surfaces always meet along a line at a perfect 120-degree angle to each other.
This specific angular relationship, known as Plateau's laws, is an immutable mathematical constant in foam structures.
You can observe these precise 120-degree junctions in any cluster of suds in your dishwater. And then something even more unexpected happens when four film surfaces try to meet. Four or more soap film surfaces can never actually meet at a single point in a stable configuration. Instead, they immediately rearrange themselves into groups of three, always maintaining those perfect 120-degree angles. This rearrangement minimizes the total surface area, effectively performing a real-time geometric calculation. It's a constant, dynamic process of seeking the lowest possible energy state within the foam. Wait until you hear what comes next about the shapes created by these interactions. When many bubbles are packed together, like in a dense foam, they spontaneously form hexagonal cells.
This six-sided arrangement is the most efficient way to tile a two-dimensional space without any gaps.
Dimensional space without any hexagons gaps minimize the total length of the cell walls, thus requiring the least amount of soap film. Think of a honeycomb, where bees instinctively leverage this same mathematical principle for maximum storage. This isn't just a coincidence. It's a fundamental property of geometry and energy conservation. But the implications extend far beyond just efficient packing in a bubble bath. These minimal surfaces, found in soap films, are mathematical marvels, solving complex optimization problems. They represent the shortest distance between points in space, curved to minimize their surface area. Scientists and engineers study these exact structures to understand efficiency in countless other systems. Every tiny mathematical decision by a soap film contributes to a larger, intricate, and beautiful pattern. These seemingly simple mathematical principles, observed in soap films, have profound real-world consequences.
Architects leverage the strength and efficiency of minimal surfaces to design innovative, lightweight structures. Imagine gigantic domes or sweeping roofs that use the least material while maximizing stability in space.
Aerospace engineers utilize similar surface tension dynamics to manage fluids in zero-gravity environments. Packaging designers apply hexagonal packing principles to create boxes that fit more product using less material. This translates directly into reduced shipping costs and a smaller environmental footprint for many industries. Biologists study these cellular arrangements to understand how tissues and organs efficiently grow and organize. The hexagonal packing in some biological structures, like the lens of an eye, mirrors that of a bubble cluster. Materials scientists investigate soap film behavior to develop advanced foams and lightweight composites. These innovations lead to stronger, more durable, yet significantly lighter materials for various applications.
From medical implants to protective gear, the efficiency of these mathematical forms is indispensable.
Understanding these natural patterns allows us to mimic and even improve upon nature's perfect designs. This demonstrates how efficiency of these fundamental mathematical forms is truths underpin the very fabric of our physical indispensable world. Therefore, the humble soap bubble provides a daily, tangible lesson in optimized design and inherent beauty. So, the next time you see soap suds, remember you are observing a breathtaking display of mathematical genius. These intricate, hidden patterns remind us that profound principles govern even the most ordinary phenomena. Mathematics isn't just confined to textbooks. It actively shapes the efficiency and beauty of our daily surroundings. If you found this exploration fascinating, subscribe for more incredible stories about the hidden world of science. Also, consider sharing your thoughts in the comments and give this video a like if you enjoyed learning something new.